Today I'm going to be speaking about the Mandelbrot set. It is essentially on the complex plane. So this is the complex plane. I have a real part and an imaginary part. And I wanted to speak about this really because it relates to my previous videos on complex numbers. So go check them out if you haven't seen them before. I don't think you need a proper understanding of complex numbers to understand the basics of this idea, but it's good to know where we're coming from. So essentially what we do with complex numbers, as I said previously, we have a real part which is like a, and then we have an imaginary part which is b times I. This is just like how many times we have I. So like we can have 2 times I, 3 times I, and so on. It gets larger. Sort of similar to an xy axis. And this vector here, or this point, is a plus bi. Now if I put a minus sign here, it just switches it to the other side. Okay, so with the Mandelbrot set, we have a function that looks like this. The z stands for complex numbers. This is some sort of constant. Now, what we focus on is basically when we input 0 and our constant value 1, what happens if we repeat this process. So another fancy word mathematicians use is iterate, but it means the same as repeat, just to make that clear. So we square 0 and we add the constant value. Then we input that again. We get 1 squared plus 1. We input what this is equal to. So this is equal to 2. So we input that value. We get 2 squared plus 1. And that is equal to, that's 4 plus 1, which is 5. So this goes into infinity. Okay? And then we think about what happens with negative numbers. So our constant value is going to be minus 1. And we are going to start off at the point 0. So 0 squared minus 1 is minus 1. So we just input that value again, we just repeat the whole process. Minus 1 squared minus 1. What is that equal to? Well, this is going to be plus 1. And plus 1 minus 1 is 0. So again, we end up with 0. And we just end up going in a loop. And I'll just show you how. So we put 0 squared minus 1. And our function never really gets larger than 2. So we're bound. We're sort of in a circle, you could think. And I'll just quickly show you how the Mandelbrot set looks. So this is the Mandelbrot set. What you may notice is that you sort of have this beautiful graph repeat in areas like here, just all around if you zoom in, and you might have seen this before and sort of the beautiful patterns it creates. Essentially, when we're inputting the negative value and we're staying inside a specific circle, you could say, or we're staying, our input values and our output values don't really change. They keep repeating and they don't get bigger than a certain number, so let's say 2. Then we're stuck in this sort of circle. Now, if our numbers are positive and they just keep getting bigger and bigger, they blow up, so our output values sort of just go all around the place. And what we say is that the function is stable in these black areas because our output values stay inside of this circle. They don't get larger and larger. But if we input values from here, our output values are going to be all over the place. They have a very chaotic pattern and they just go into very large numbers. So these numbers, this looks very big, but essentially on the graph it's like the input values are very small, like 0.2, 1/8 or 1/4, just really small values so that our numbers don't blow up essentially. What we also look at are the edges of this function, because this is really the point where the chaos begins or ensues. And that's really the interesting part of this function, is when do we start getting crazy output values that just go into, you could say, infinity or into very large numbers, and when do our numbers stay inside of a certain bounded area and have some sort of pattern. Well, it's really hard to know, because obviously you can zoom in as much as you want on this, but really inputting a value from here is going to be really hard, because you are really never going to precisely get it, because if you just keep zooming in and keep zooming in into infinity, you will never get a precise input value, if you know what I mean. To get a precise output, it's always going to be a rough approximation. Um, these fancy looking objects are called fractals. You might see them in nature. Certain plants sort of create their flowers or arrange their flowers in a specific way, which sort of resembles mathematical graphs, you could say. This is all for today's video. I just wanted to sort of show you a popular function, a popular complex function, and the beauty of it, really, because this is a beautiful graph. Okay, so thank you for watching. Please check out my other videos on complex numbers. Comment, like, and subscribe, and please give me your opinions on my videos. I would really appreciate that, and tell me which topics you would like to see next. Thank you and goodbye.